In this video, we're going to circle back to the definition of limits, and we're going to start adding some precision. So this is a more formal or precise definition, or really definitions, plural, of limits. We're going to look at it in two different ways. So first, we're going to talk about some precision in definitions in mathematics in general, why we need that, and then specifically we're going to look at it in the context of this idea of the limit of a function. Where do we need precision? What's going on in our current preliminary definition? And then we'll take a look at two different ways of adding that precision. We'll look at distances measured, and we'll look at open intervals, and hopefully those kinds of little buzzwords will start making a bit more sense once we take a look at them. So here's in general the need for precision in definitions. If we look at this specific definition here, this is the one that we've been working with, right? Where our function is defined around some value, except maybe not at the value itself. And then we say if the y values, the outputs, f of x is arbitrarily close to some single real number L whenever x is sufficiently close to a but not equal to a, then we say that the limit as x approaches a of f of x is equal to L, blah, blah, blah. Now, this is a pretty good definition, all things considered, but there are a couple of spots that are a little bit ambiguous. What does it mean for f of x to be arbitrarily close to something? And similarly, what does it mean for x to be sufficiently close to something? These kinds of closenesses we tried to talk about at the very, very beginning of this series of videos, where we talked about arbitrarily close is like if there's an infinite number of possibilities for what close means, then arbitrarily close means it beats all of those standards of closeness, right? And then if something is sufficiently close to A, it means it's close enough to do something. So we hopefully have some intuition about what this means, but just writing it down isn't really enough to impart that intuition. We have to talk about it a lot. We have to kind of unpack this definition. In mathematics, we really like our definitions to be precise enough that they can essentially stand on their own. Now, that's not always easy, and we'll find that in this case, when we start adding some precision in these definitions, they do stand on their own, but they become a little bit less intuitive at first, because what we're going to do is, instead of using the ambiguity of arbitrarily close and sufficiently close here, we're going to start adding some notation, some kind of mathematical expressions that really formalize this idea of arbitrarily close and sufficiently close. So here's what we need to do in our specific context. In order to talk about these limits precisely, we need to do a couple of different things. We need to first choose how we're going to measure close in a general sense. What does that mean? Not only what does close mean, but how do we measure that kind of a thing? And this is where we're going to get into the idea of measuring distances and looking at open intervals or open sets. Then what we're going to do is we need to set up an arbitrary measurement of that closeness. That's, again, because f of x needs to be arbitrarily close to L. And we're going to use that as a kind of boundary, and then we're going to go backwards and show that we can find x values that are sufficiently close or close enough to A, such that the outputs of those x values are within this measure of arbitrary closeness. Whew, that's a mouthful. So this is kind of a weird idea, but we've got three tasks in general. Again, come up with a way of measuring closeness, figure out a way of arbitrarily defining this closeness for f of x and L, and then go backwards and show that we can always find x values that are within some measure of closeness to A, such that f of x is within this arbitrary measurement of closeness with L. So here's kind of a picture that we're going to be looking at here. This is a hard picture to understand at first, but we'll start off with a couple of different things. Green is going to be good and red is going to be bad. So what this means is that in the second picture, we found x values that happen to be close enough that the y values are within some range of closeness. Now you can see these red dotted lines on the vertical axis. I'm going to say that that is our arbitrary measure. Maybe I'll use red and dotted lines here. That's our arbitrary measure of closeness. So we're saying any y values that are within these bounds, these red dotted lines, we're going to call those close to L. Now notice we haven't really addressed this first part yet. I haven't figured out how we're measuring that other than saying, like, all right, within these boundary points. So We're looking for y values that are within this. And what we need to do is find x values that are close enough to a, that's represented as this yellow interval of x values, that when we trace all of these x values up to our function and then follow over to the vertical axis, the y values need to be within this little measure of closeness. Now here we can see clearly they're not, right? We've looked at our x values here on our axis, and we grabbed this chunk of them, and we brought them up to our function, plugged all of these x values into our function, and the corresponding y values were way out here. Too big. What we wanted is that all of the y values are within this arbitrary closeness. So what we do is we shrink our interval of x values. Here we go. Make it a little bit smaller. Bring this up to our function. Throw all those x values into our function, find the y values, and look at that. All of these y values are within this little range, we can say, that we defined as close to L. What we need to do is to show that this is able to be done no matter where these red dotted lines are. So I have a little activity applet thing that we can look at. What I want to do is compare two different limits. One of them is going to exist and one of them won't. Let's start with one that does exist. This is the picture that we were just looking at, but you'll notice that there are some sliders on the outside here. We're going to be able to play with this a little bit. So what I can do is I can move my red dotted lines here up or down, and this is essentially me setting up this arbitrary closeness. So if I had a really loose standard of closeness, I could say, all right, any of the y values within this big range, we'll call those close to L. And then we just need to set some interval of x values, it doesn't matter where they are, and all of those x values give us y values within that range. Now what we can do though is be a little bit more picky about our interval of y values. Maybe I'll bring them really close to each other, and I'll say, no, I have to find x values that are going to give us y values within this tiny little interval, just circling around whatever L is. Now you'll notice I have to see if I can bring my interval of x values close enough to A. Notice I'm dragging this line close to A, but what I'm really looking at is the corresponding y values. Trying to make sure that those y values are actually going to be within that interval. Now, all we're doing here is we're giving some clues that in this function, we'll always be able to do this. If I shrink this red interval, or these red kind of standards even more, bring them really close, then what I need to do is to suck my x values a little bit closer to A, and look, you can barely see that turned green. I found x values that are close enough to A so that the y values were within this arbitrary measure of closeness to L. Okay, so that's what this looks like. We can bring this arbitrary standard of measurement out, and then it doesn't really matter where our interval of x values is. It can be pretty big because the y values are going to be within there. But let's take a look at an example where that limit doesn't exist, where we're not able to do that. So we'll scroll down a little bit, and here we go. Okay, so we've got this piecewise defined function, and hopefully we can just look at this graph and say, sure, the limit at A does not exist because the left side limit and the right side limit are not the same thing, right? Hopefully we can see that. So what we're going to do is we're going to set up a measurement of closeness to L. Maybe first I'll start off here. For some of these measurements of closeness, if I have a pretty wide one, you can notice that I can find an interval of x values. There we go, I did it, where the y values are within that range. But I have to be able to do that for every interval of y values, or for every measure of closeness. So what I'm going to do is just find one where I can't do it. I'm going to go ahead and I'm going to bring this top boundary down a bit. And what you'll notice is that all I have to do is to bring that within this little gap here. And suddenly, no matter how close I bring my x values to A, I can't get my y values to be within this arbitrary measure of closeness to L, because some of them are still outside of there. And I'm never able to get these y values up here inside this little range that we have set up. Since we can't find an interval of x values that will make our y values within this arbitrary measure of closeness to L, that means the limit doesn't exist. Hopefully that's a helpful way of describing what we're talking about here. But let's go ahead and get into the definitions. We have two different options of doing this. The first is to just straight up measure distances, and the second is to use open intervals. I'm going to be upfront and honest. I really like the open interval interpretation of this, although the measuring distance one is pretty standard to see at this level. Just for a brief glimpse. Really, this is the difference between two fields of math that are really closely related. One of them is analysis, and one of them is topology. Analysis uses this measurement of distances, and topology uses this idea of open sets or open intervals. Anyways, let's talk about measuring distances. So what we need to do is to talk about two different distances, right? A distance in the y direction and a distance in the x direction. So let's talk about our arbitrary closeness here. What we're going to do is we're going to try and find a set of y values that are within a certain distance of L. So if I trace, let me clean that up. If I go ahead and I trace a straight line in here, and if I look at this set of y values, I'm going to notice that they are within a set distance from L. A distance above L and a distance below L. What I'm going to do is I'm going to call that distance epsilon. The Greek letter epsilon, it kind of looks like an E here. Then I can notice I have a corresponding distance in the x direction. I'll draw my vertical line now, and you'll notice that I have these distances here. They aren't actually the same in both directions, so I'm just going to take the biggest one, and I'm going to call this delta. So there's an epsilon above L and an epsilon below L, and then there's a delta on the left of A and a delta on the right of A. So we have this kind of like symmetry, right? We have like L plus or minus epsilon, and over here we have like A plus or minus delta. That's giving us our intervals of x and y values, or our sets of x and y values. Now, since these are distances, what we want to say is that our x values are within this little, I don't want to call it a domain, but this little interval here. They're within a distance of delta from A. And our y values are within this little range, a distance of epsilon from L. Well, and that's pretty easy to do if we remember how to measure distances. We're going to use absolute values. So what we're going to do is we're going to say the distance between our y values and L has an upper bound of epsilon. And similarly, what we're going to do is we're going to say that the distance between x and A has an upper bound of delta. We're also going to add a lower bound here. We're going to say the distance can't be 0, because remember in our original definition of the limit, we said that we're looking at x values around A but not equal to A. So we can't make the distance between x and A 0, or else those two values are equal to each other. So we'll just say, okay, between 0 and whatever delta is. These are the two distances that we're going to be looking at. All right, here's our definition of the limit of a function, and you can see these absolute values getting tossed in here. We'll read it through and we'll try and unpack this. So the beginning seems pretty similar, right? Suppose the function f is defined for all the values x in some open interval containing a, but maybe not a itself. Seems reasonable. We've seen that kind of language before. If for all epsilon greater than 0, there exists a delta greater than 0, such that the absolute value of f of x minus L is less than epsilon whenever 0 is less than absolute value of x minus a is less than delta, then the limit as x approaches a of f of x equals L. Oh my goodness, there's a lot going on here, and it is very easy to fall off the rails quickly. So let's talk about what this does. Okay, so we're going to say for every epsilon, remember, that was our distance this way. We're saying for every distance of what it means to be close to L, that's what we're really defining here, right? This is an arbitrary measure of closeness. We're going to say our y value is close to L if it's within this distance, and we'll call that distance epsilon. And everyone's got a different idea of what it means to be close, but we're going to say for all epsilons greater than 0, for every idea of what it means for a y value to be close to L without ever actually equaling it, then there exists some other distance, this delta greater than 0. We have some other measure of closeness such that when we look at these x values, we get y values that are, we'll say, close enough to L. And maybe I'll actually not say close enough, I'll say arbitrarily close. Arbitrarily close to L. Because remember, we're just picking any random standard of closeness, epsilon, out of a hat. And we're saying, all right, if the distance between the y values in L is less than any epsilon, all epsilons that are greater than 0, notice it has to be greater than 0 because we can't have an absolute value less than a negative. So we're going to make all of our distances positive, and we're going to say, if for any distance that you pick, I can always look at y values that are closer to L than that distance, that's arbitrarily close to L. And then we're saying that happens when x is within this distance of A, whenever x is sufficiently close. And notice we have that it's not actually equal to A because that distance has to be greater than 0. Okay. That's the analysis version, the epsilon-delta version. What we're going to do now is we're going to look at an open interval version. And this is my favorite. I like this because what we're going to do is instead of measuring a distance, we're just going to say, what if we just grab an open interval of y values? And we'll say, I don't know, make sure that L is in this interval, and we'll call this an interval from P to Q. And it's got to have L inside of it. And if you pick any interval that way, then we'll say any of the y values in that interval are close to L. Okay? And then to do that, we need to find x values that are within this interval. I'll call it an interval from C to D. C and D are going to be my x value intervals, and P and Q are going to be my y value intervals. And you can use whatever letters you want. It doesn't really matter. But we're going to say that if you find y values that are within this red open interval, arbitrarily chosen endpoints, P and Q, doesn't matter what you make them, but P has to be less than L and Q has to be bigger than L because L's got to be in that interval. Then, if you find y values in there, they had to have come from an interval of x values between C and D. Here's what we've got. If for all intervals P, Q in the range of f, meaning these are actual y values from our function, that's what it means for it to be the range, they're outputs, that contain L, so L is somewhere in that interval, there exists an open interval, C to D, around x equals A, in the domain of f, such that for all the x values in that open interval here, the y values are within this open interval. So basically what we're saying is all the x values in here, we can trace them up and get all the y values out here. And whoever wants to set up this red interval of y values can. As long as you make it any open interval around L, the limit exists if we can always find an open interval of x values. This, in my mind, goes right back to that little applet that we were playing with where we were changing the sliders, right? I like this because we can make those sliders in our minds to change the interval of y values, and then we just have to find an interval of x values that goes with it. So let's go back to this picture here really quickly, and this is how this goes. We're going to change this interval, and we're going to say, all right, here's P right here, and here's Q right here. I've got a pretty small open interval of y values. And now I'm going to say I need to be able to find an interval. I'll move C and D such that for all the x values, the yellow ones, in this interval, the y values, this green bar, are within this interval. So that's what the topological definition of a limit is, the open interval version here. We're going to look at both of these versions, and we're going to see if we can set up a proof to prove one or two pretty basic limit statements, things that we understand pretty intuitively now because we know how limits work, but we'll be able to kind of prove these rigorously using these definitions. These definitions might seem a little ambiguous and weird, and they kind of are, but what you'll notice is that most of that problem is in the weirdness of the notation, not the ambiguity of the wording that we're using. And that's really the point of these definitions. We want to get rid of that ambiguity that we had with this idea of arbitrarily close and sufficiently close. We're trying to formalize what that really means. All right. Check out the video a little later on for when we actually prove some limit statements, and then we might do a little bit more with that. Hopefully that's helpful to clean up some intuition for everyone.